The most powerful computer you own has zero security. No, I'm not talking about this one. This one is a fortress by comparison. You have dozens of applications spread across the device with no insight into what the others are doing. No, I'm talking about the computer in your head. The thinking part of your brain has no permission system. You can't just pause your own heart just to see what happens, although that's somewhat debatable of a fact. But the layer above that, where actual cognition happens, has no barriers. Thoughts can examine other thoughts, interrupt them, or even reason about them. Even you watching right now can internally debate what I'm talking about. You're not just blindly accepting input. You can take a concept and play around with it. You can even think about the fact that you're thinking about this sentence. Try, pause the video and think about it. That little line of recursive thinking that you just did there, what cognitive scientists would call introspection, almost no computer has the ability to do. In the 1980s, some of the smartest researchers tried building a machine that could, and it worked. It was literally decades ahead of its time, but it was also inadvertently the least private and most insecure operating system ever created. It was so open that no one ever tried to build anything like it ever again. But fragments of this superpower still remain inside many of the modern programming languages that we use today. This is going to make the Rust people very angry, the Java people weirdly proud, and the C++ people more optimistic about the future. Patty Moss, 1987. Computational reflection is what a system does when it reasons about itself in a causally connected way. That was a heck of a sentence, but just give me a second and I promise you'll understand something super cool. Begin cloning process. This is me. Or was me 10 seconds ago, and that's kind of the problem. It's information, but it's not causally connected. If I do something really silly, like put on this crazy hat, the problem is the representation of me doesn't also update. I can even take a pen and draw a mustache on the photo, and sadly, nothing appears on my face. This isn't a reflection of the current reality. It's really just stale information. But a mirror, well, a mirror is different. If I change, it changes. It is causally connected information in one direction, kind of without the boy band reference. This still isn't quite what Moss actually meant because a mirror is passive. It can show me what I'm doing, but it can't actively participate in what I'm doing. But imagine we had a magic mirror that worked in both directions. If something happens in the reflection, then it also happens to me as well, the original representation, wired back into the very thing that it reflects. And that is exactly what Patty Moss meant. Well, here's the annoying part. Almost every program on your computer is a lot closer to the Polaroid. And I can tell you this from experience because otherwise, my career wouldn't exist. Conceptually, reverse engineering is kind of equivalent to performing introspective surgery on a patient who can't do it himself. Most programs are like zombies. They run, they react, they do things, but they have no understanding of what they are. It's kind of weird to think about, but programs don't know I'm a class, or this memory is this player's health bar. Zero self-awareness. Much of my job is strapping programs to a table, hooking them up to debuggers, and reading through their thoughts from outside the program space. Every single tool that exists in my field, like disassemblers, decompilers, even debuggers and stuff, exist to try to take that information that was lost during the journey down over to machine code and be able to reconstruct it. And also, have you ever used a cheat engine before to give yourself infinite gold or whatever? I remember there was a cheat in The Sims and you could just give yourself infinite money. It was awesome. And that's not the point of The Sims. The point of The Sims is to do crazy stuff and try to get the Grim Reaper to We're basically simulating reflection in a very hard way, kind of after the fact. I mean, that's why it's called reverse engineering, is because we're effectively working backwards. But what if programs were so smart that they could do surgery on themselves? Would you trust me as your surgeon? Don't worry. I promise my hair won't fall into your open liver. I look absolutely insane right now. It's All right, we've got a great lineup for you guys tonight. Let's go over to our returning champion. Where would you like to start? Our categories are Before They Were Giants, Potent Protocols, Keyboard Confessions, Winter is Coming, and Domain History. All right, your clue is, on March 15th, 1985, this company registered the first .com domain in internet history. I'm waiting. Your possibilities are Apple.com, IBM.com, Microsoft.com, or Symbolics.com. That is correct. The answer is Symbolics. I really like having this microphone. It's like, yeah, listen to me. I am saying something important. If I just walked around with a microphone, would people listen to me more? They'd probably think I was nuts. There's a good chance that if you're around my age, you probably haven't even heard of this company, but the entire hype behind it centered around this idea that quote-unquote expert systems, which was like a kind of early rule-based AI system, would replace doctors, lawyers, etc., all within the next decade. Symbolics, and the US as a whole, was in this kind of mad, fierce race with Japan's 5th-generation computer system to create the world's dominant AI machine. Sounds a bit familiar if you ask me. If you ignore the eventual economic failure that Symbolics became, they did have some really early on kind of quirky ideas. The whole idea around the company was selling these like super expensive Lisp machines. So this is custom silicon designed specifically for a single programming language. That would be like today having a custom machine dedicated only to running Python. Anyway, Symbolics realized that you can't just sell a box, you have to have an operating system that goes along with it. Which brings us to Genera, the most powerful and least private operating system ever created. Weirdly, one of the better ways to describe the complexity of this operating system is just to take a look at the keyboard and see how many modifier keys it has. You've got Control, Shift, Super, Hyper, Meta, all of these additional ones, and you have to like contort your hands in crazy directions to try to hit all of the modifier keys. Like, I'm just doing gang symbols over here. Watch this. Am I doing it? Ooh, magic. Genera was, and I really do mean this, just a fantastic operating system conceptually. Everything on your screen was a live running object, and you could just click on it and inspect the live executing source code corresponding to that object. So you didn't have to wait around for compilation, there's no concept of user space, kernel space, everything, you just click on it and you can inspect it, and you can even dynamically modify it. You want to change something? Anything, just do it. In our modern concept of programs, the compiler is king. The compiler knows absolutely everything. It knows the types, the functions, the class names, all of the identifiers inside of the application. But once we move on to the actual executable binary portion of this, the majority of that information is just tossed away because we don't need it anymore. It's kind of like that Polaroid that we took previously. We used to have this entire machine code representation of the program. But Genera did things a little bit different. Genera didn't throw out any of that information. It's this perfect example of a fully reflective operating system because all of that metadata stayed live in memory attached to every different live object executing on the system. So it's just like that magical two-way mirror from previously, because not only is it a live representation of an object, but it's also an editable representation. So that means that any process executing on the system can modify any other running process. This kind of makes for some weird properties that no other operating system really replicates today, and for good reason too. For example, let's say you have a program that crashes on the computer. Well, in Genera, it doesn't really crash necessarily. It might be in a bad state, but it's kind of still there, existing in memory. So what you could do is you could just walk over, live patch the function that is causing the crash, fix it, and then then it runs and continues on its day. Fans of Genera often reported running their system for months or even years without rebooting, which just sounds like absolutely nuts to me, but it does sound really cool because they could just be live patching their underlying operating system during execution. And in a lot of different ways, it kind of sounds like a programmer's dream. But if you've been paying attention, and like really paying attention, you've probably noticed something. Keith's watching you. If you're paying attention, do not disappoint. If any code can touch any other code and there's no walls in between programs, then nothing is stopping, for example, your mail application from silently reading, say, your banking application and getting all of your credentials. Or even another program could just go boop, recompile another program on your system, and you would have no idea. It would be incorrect to say that Genera had weak security. Genera had no security. It truly is the least private operating system that was ever created. And the best part is it was completely intentional. Like, this was all by design. And you might be thinking to yourself, like, what? How could a company like this possibly have made it? But you have to think to yourself that the concept of malicious code wasn't really as much of a thing at the time. Malware wasn't really that much of a thing yet because the internet wasn't really much of a thing yet, so nobody had this mental model of it. And so you have computers that are also like hundreds of thousands of today's dollars, and researchers just kind of trusted each other. And side note, if you're interested in learning about trusting trust, go watch my previous video on the original sin of computing. So like, yeah, nothing was technically preventing somebody at Stanford from just going through and modifying the computer of somebody at MIT, but nobody really did, because even the concept of the word hacker didn't really have the same connotations that it does today. It more just meant somebody who really loves exploring. And even the company Symbolics, who created Genera, ended up failing mostly just for economic reasons. Although it is interesting to speculate, if we still had the concept of Genera today, how that would fare in the modern era of the internet. Ironic that the first .com in history built the operating system that was fundamentally incompatible with the internet. Unbelievably powerful, but never attempted again. Symbolics ended up collapsing, and although you can find emulators of Genera, it's really just semi-abandonware at this point. But the whole idea behind it ended up escaping containment. You inevitably had hundreds of engineers leaving and going to different parts of the industry, and this obsession with reflection followed them to their respective industries. This made it into different languages, different runtimes, different language committees. Some got a full dose of reflection, some got a partial dose, and then some like purposefully stayed away from it and stayed immune to it. All right. I think it's time for a tier list. Now, just to be clear, Symbolics didn't actually invent the concept of reflection themselves, and it's kind of a hard question to answer of who actually takes the crown for this, because depending on who you ask, it could be Brian Cantwell Smith, Xerox PARC, Patty Moss, John McCarthy, Turing, Newman, or even Goodall. But it is safe to say that Genera was one of the purest forms, taken to the logical extreme of the concept of it, and you can actually kind of rank what I would call the reflective IQ of a programming language based off of Moss's definition. This would include 1, how much does a running program understand about itself, and 2, how much can it act on that information? Keep in mind, these are my personal opinions, which is synonymous with objectively correct, right? Start with C, first language. Now, I'm sorry, C has to be F tier. You just have no introspection capabilities. You have no insight into what the compiler actually knows about your program. If you want to traverse all of the members of a struct, for example, you're going to have to manually list out every single one because the compiler's not going to help you. Next one, Java. And Java is actually pretty darn good in this particular area. Keep in mind that Java is compiled over to bytecode, and then the bytecode runs inside of a virtual machine, or the JVM, the Java Virtual
virtual machine to be exact. So Java is kind of this amalgamation between interpretation as well as compilation down to underlying native code. And I personally really like Java, but in this particular case, the good thing about it is it has a very powerful reflection API. Using the Java reflection API, you can just go through and say, hey, what kind of methods does this particular object contain inside of it? And also you can go through and dynamically invoke them as well. The one thing that Java is missing is you cannot dynamically add or delete methods while the program is executing. So because of that, I don't think it's deserving of the highest tier. And I know one of you crazy commenters out there is gonna be like, oh no, you can do this crazy out-of-pocket hot swapping technique and directly modify the bytecode inside of memory and actually do your class manipulation. I mean, like at that point, you just have to call it quits somewhere. Like what if you take a computer and just shake it at that point and change the bits physically? How about them apples? I'm trying to rank based off of the core intent of the language, not in kind of hacky techniques. B tier. Okay, next language. Common Lisp, once they added the object system class. And this is gonna be the highest ranked kind of realistic language. There is another language that is technically ranked higher, but I'm saving this one. And it's more of an academic-ish type language. This is what Genera was written in, and it has everything. You have meta objects, you're able to dynamically redefine functions on the fly. It's actually just kind of crazy. And it has what computer scientists call homoiconicity, which means that any program that you write in Lisp is itself actually a Lisp data structure as well. That means that you can infer the entire anatomy of a program if you're just reading in the Lisp data structure. Now let's move on to the dreaded C++. And it's a little bit complicated in terms of reflection, but I'm going to come from this from a C++ 26 perspective. Now C++ 26 has brought a lot of new features, and one of those new features is static compile time reflection, and that is very exciting and very cool. But there's a couple distinctions that we have to make. So we have meta objects, and we're able to perform introspection on the structure of a program, but all of this metadata and information disappears at runtime. So it's only available to us during compilation. In other words, you can write C++ code that executes inside of the compiler. You can use the meta functions to query things like how many non-static data members are present inside of this particular class, and that metadata is available to you. But the thing is, all of that metadata disappears after the compilation process is complete. That's a little hint, some foreshadowing about a project that I very recently presented at a conference, and I'll get into that in just a second. So going back to our tier list, I'm going to give C++ 26 reflection a D tier ranking. We are a lot better than C. We actually have introspection and meta objects and stuff, but we're just not as high as other languages. Python. And this one was a little bit surprising to me. So I'm more of a C++ developer at heart. I can write Python, but I'm not like super deep into their ecosystem. But if you're clever and you're a super deep Python developer, you might realize that Python is an interpreted language. And since it's an interpreted language, we can probably do some interesting things at runtime. But the real question is it better than Java? Is it worse than Java? Or is it about the same level of reflectiveness as Java? You can pause and see how smart you are. It is more reflective than Java. It is A tier, as much as I hate to admit it. There is this concept known as monkey patching, where you can alter the actual class during dynamic program execution. And there is a stipulation that this is generally not recommended for standard application logic, but you can see how it might be something useful for unit testing, for example. So in general, Java is structurally immutable, and Python is structurally mutable, even if it's not really encouraged. I stand by A tier. It's time to address the elephant in the room, or rather, the crab. You know, I don't actually have a crab plushie. I've got Keith, I've got Duke over here, I've got a Flareon too, an android, Buzz, whatever this cat is called. I don't know what. It's got a particular name, I don't actually know what it is. I also have more on the ground too. I have a lot of stuff around me, but I do not have a Rust crab. This one may surprise you as well. So both Rust and C++ are zero abstraction compiled languages. But only C++ has native built-in static reflection capabilities. If we bring up the phases of a compiler, for example, C++ static reflection happens after semantic analysis. Now in Rust, you can have macros and stuff, but this is happening before semantic analysis. You do not know anything at the parsing step. It's kind of akin to you're trying to edit an essay, but you don't actually know what any of the words mean, so you can do like simple find and replace for letters, but you're basically just like throwing spaghetti at the wall and seeing what sticks. Je n'ai pas compris. That was a terrible French accent. My French teacher would kill me for that. So these limitations, combined with the fact that if there's no static reflection, there's no runtime reflection as well, mean that we're gonna give this F tier. It is actually a little tiny bit better than C, but not enough to really bump it up to another category. Interestingly enough, this puts our most memory unsafe language and our most memory safe language on the same tier level for reflection. Very interesting. Go is C tier. There is runtime type introspection, but it's like kind of annoying to use. And if you don't believe me, then you can go check it out yourself. Lastly, but clearly the strongest, we have Brian C. Smith's 3Lisp, and this is SS plus tier, easy. And 3Lisp kind of teaches us an important lesson here. So 3Lisp is not truly its own programming language, it's a derivation of Lisp, but kind of a hint here that you can basically take any language, and if you're smart enough about how you write the code, you can manually raise it up like at least one level on the reflection tier list. 3Lisp was part of Smith's PhD thesis where he described an infinite tower of meta-circular interpreters, infinitely high invocation by God himself. And I'm not actually making that up because you could go check his code comments and see all of that. Man, programmers make me laugh. The correct definition is that the infinite reflective tower means that a program can reify its own interpreter mid-execution and change the semantics that it's running under, which is basically just a crazy way of saying that a program can change what the definition of running is while it's actively running. The main difference is that with Genera and Common Lisp, you can modify what is actively running, but you can't change what the concept of running is itself. So I'd kind of compare this to lucid dreaming. This is the moment where you realize you're in a dream and now you suddenly have the ability to change how gravity works. You're changing the definition of reality. Anyway, you should really go check out his thesis because it's very interesting to read because it like only partially works. So theoretically you're working with infinite towers, but you don't really have infinite towers of server racks of hardware to work with. It's all going to be finite hardware. So there's actually a lot of cheating that is involved inside of this concept. It's kind of like if you're working in your dream and your dream is extending as you're looking around and only doing that when you actually look at something. Now it's time for the moment of truth where I reveal the secret of how to raise any language up about one tier. And this is exactly what I've been doing to C++ with my new library, CallMeMaybe. We can bring C++ up to C tier. This is my brand new open source tool that I just recently released built on top of C++26 called CallMeMaybe. So what it's doing is it is implementing runtime reflection on top of the static C++26 reflection. And I just recently presented this research over at ACCU on C, which is a really cool C++ conference over in the UK. And if you have a chance to check it out, you should definitely attend that conference. When I was there, I was presenting all of this research and it was so scary because I'm building on top of other people's research that's released inside of the actual like C++ standard now, and a lot of these people are sitting there in the audience watching me, and I'm explaining how their features work kind of to them. But yeah, it was an interesting experience. I had a lot of fun. Those people are really nice. If you'd like to use or try any of the code in this, I'm going to put a link to it in the description below. The coolest thing is that if you actually want to go see the paper for reflection, you can go over to the P2996 Reflection for C++26 proposal. And if we go down here, we can take a look at the introduction. The interesting thing that I want to talk about here is this is proposing static reflection. So remember, this is a feature that is happening during just the compilation process, and all of this information is only available at compile time. So what I wanted to do with this research and with this project is have this kind of bridge that allows us to get this information also at runtime. A few of the main interesting features of C++26 static reflection is, first of all, this std meta info. And this is kind of an opaque handle. So it's this ID system into the compiler itself. So each ID points to a node inside of the compiler, and each of these nodes represents something inside of the syntax. So next we also have the reflection operator, and it's this double caret here. Okay, so funny story, when I was giving my talk for this, afterwards somebody raised their hand and corrected me and said this is actually called the cat ears operator. So I think somebody actually wanted to name it the cat ears operator because, you know, caret caret. But it is officially not the cat ears operator, sadly. What the reflection operator does is it takes in regular syntax and it raises this into the reflection domain. So now we're working with that kind of mirror that represents ourself and represents the original syntax. But you have to have the kind of inverse of that. So what we have is the splice operator and brings us back down into regular syntax. So they're kind of like this endless circular loop back and forth from each other. So you might be asking yourself, okay, what is the thing that forces us to stay working inside of the compiler? Like, how can you tell the programmer what to do that you're not allowed to use this particular function or thing during runtime? How do you enforce this? Well, there's a special keyword here called const eval, and this is associated with all of those meta functions that belong to C++26 reflection. So if you mark a function as const eval, it is forced to execute at compile time. This is the Clang implementation of C++26 reflection inside of the actual Clang compiler itself. You can see we have all of those keywords that we talked about previously, like const eval, to force this to execute at compile time. And we also have our info, which is our ID into the compiler that identifies what syntax we're working with. Now the compiler has kind of provided us all of this free information and metadata, so we can kind of ask it about itself. We can pass in an object and say, what is the type of this object? We can pass in a class and say, what are all of the non-static data members that comprise this particular class? And the compiler is also giving us rules. It's like, I'm laying down the law. I've got this const eval declaration over here. You are not allowed to take this information after compile time. Personally though, I really do not like to be told what to do, which is why I built an entire library just to break all of the rules. I created my own entire custom registration system for runtime reflection. So you can see this is registering a class, and it's taking in the compile time reflection and kind of converting it over to a runtime reflection object. And you see every time we have this std meta, that means we're using those C++26 features to build on top of it. This is just my registration class, by the way. It goes on for freaking ever. This took a lot of work. Oh my gosh. The best part is that as I was developing this, you actually don't know if it's you making a mistake or the compiler making a mistake, because all of this was completely experimental as I was writing this library. Fortunately for you, however, I have done all of the heavy lifting for you proactively. So all you need to do in order to use runtime reflection is annotate your functions inside of your classes with my custom CMM, CallMeMaybe, reflectable annotation, and then you can automatically register all of them for reflection. And not only that, I am extremely picky when it comes to API design. I think that APIs should be beautiful and kind of speak for themselves. So what I did is I decided to mirror the meta functions. So it almost exactly copies C++26 already. You see I have the info object as well, which is my custom scalar type that returns the non-static data members, which should look just a little bit familiar. And with that simple, it's not really simple, it's like, that was kind of a lot to work on, but with one single library, we can effectively raise C++ or any language from a lower tier level in the reflection tier list up to a higher level. Now, I think the really kind of counterintuitive takeaway from all of this is that computers are usually defined by what you can't do, like what you're not allowed to do. You can't touch this memory, for example. You can't modify this object at runtime. But what I really wanted to show is that with just a little bit of creativity and work, you can greatly exceed the original intent and limitations of a language. You know, sure, there's going to be some trade-offs, but that's kind of what makes computer science so interesting and fun. And to me, reflection is one of the most interesting and complex subjects that you can actually learn in computer science. So what are you waiting for? Go find your favorite programming language and raise it up one tier on the reflection tier list. You might surprise yourself how far you can go. As always, thank you so much for watching, and until next time, Lori wired out. We're gonna do a C section. Hope my knife isn't rusty. Gonna need some Java to wake me up for this surgery. Oh no, a Python. I don't think I can slip that one in naturally. Oh my gosh. I like to do my incisions in a zig-zag. I can't think of a single other programming language right now. Lua? How the heck can you get Lua into anything?